Hello everyone, I'm Saad Khan and I'm a sophomore at the Department of Mechanical Engineering in IIT Bombay. And today we'll be learning about eigenvalues and eigenvectors, which is a part of the linear algebra course which is taught in the second semester at IIT Bombay. So from the industry standpoint, matrices often pop up in many applications, most of them being in machine learning, artificial intelligence, state estimation, control theory. Now, in many of the applications, matrices themselves are not as useful as they might look, but there are some of the properties are what are of interest. So these properties are captured by their eigenvectors and eigenvalues, and these eigenvectors and eigenvalues can be used to characterize a matrix completely. All right. A very popular algorithm in that domain would be a principal component analysis algorithm. That algorithm is used in image processing to distinguish between the features of an image between two different directions of that image, right? This algorithm primarily makes use of eigenvectors. So let's try to understand what eigenvectors and eigenvalues are. So we know that matrices act as transformations on vectors. They transform a vector from one vector space into a vector of another vector space. Now, this effect of the transformation can be that of elongation, compression, or rotation, or a combination of all these three, right? Basically, you may have your vector being stretched and rotated at the same time, or just being stretched or compressed, or just being rotated. Any of these three would be possible. But for square matrices, it is really important to observe that this is strictly for square matrices, that there may be some vectors V. There may be some vectors V such that when A is operated on these vectors V, the result is a vector along the same direction as V, but it may get elongated, compressed, or remain the same. All right. So to capture it geometrically, if this is your 2D plane and this is your vector V, when A acts on V, it gets transformed into a vector AV. All right. So we're looking for vectors V such that when A acts on them, the resulting vector AV is along the same direction as V. It may even be in the reverse direction. So we can write that AV will be some constant times V. This constant may be negative. Right? So this equation here, you saw this equation here, AV equal to lambda V. This is called the eigenvalue equation, right? All this says is that there may be vectors V that upon being operated by A get transformed into a vector V, into a vector W, my bad. That W will be along V and that W can be written as lambda V. So if we look at this equation yet again, AV equal to lambda V and plug in V equal to 0, we get 0 equal to 0. Well, this is the solution that is not of interest to us. So we trivially ignore it and we stick for the non-zero vectors V that are the solutions of this equation. All right. The non-zero solutions of the eigenvalue equation, are called the eigenvectors of A. All right. The eigenvectors of A. And the factor by which they get compressed or scaled is called the eigenvalue lambda. All right. So V will be the eigenvector and lambda will be the eigenvalue. So now that we understand what eigenvectors and eigenvalues are geometrically and mathematically, we will proceed to find eigenvalues and eigenvectors of a matrix, of a given matrix. All right. So how to do that? If we have a square matrix, I would like to stress on this again. Eigenvectors are defined only for square matrices. This is a very strict constraint. Given a square matrix A, we can compute their eigenvalues by starting with the eigenvalue equation, of course, and then subtracting lambda V on both sides of this equation. If we do that, we get AV minus lambda V equal to 0. Now, if we take V as the common factor and take it out, we get A minus lambda I times V equal to 0. All right. Here I is the identity matrix, which is the same order as A. So now that I know that A minus lambda I times V equal to 0 for eigenvectors, and we are interested in non-zero V. All right. Non-zero V's. We are interested in non-zero V's. So we will find out the other alternative, which is equating the determinant of a minus lambda I to 0. Because if v is non-zero, the determinant of a minus lambda I must be 0. Alright. So if we solve this equation, we get a polynomial in lambda, which equate that to 0, and then solve for the roots of that equation. We may get more than one eigenvalues, which is natural. And upon solving this equation, we will get the eigenvalues. Now, how to find the eigenvectors? Just plug your computed lambda. Let's say that you found out the roots of the eigenvalue equation were lambda 1 and lambda 2. You want to find out the eigenvector corresponding to lambda 1. So you plug your lambda 1 in this equation. Now this is as simple as solving a linear system of equations. Alright. So this is something that we've been doing all our life. So let's try and compute the eigenvectors and eigenvalues of this matrix. Alright. So we'll start with the a minus lambda I times v equal to 0. Then we will equate the determinant of a minus lambda I to 0. Alright. And then first of all, we'll compute the a minus lambda I matrix, which is just going to be minus 1, 0, 3, 7 minus 0. Alright. Now that I is the identity matrix and it has 1s along its diagonal and 0 everywhere else. So when lambda is multiplied with I, we get lambdas along the diagonal. And computing this difference, we get minus 1 minus lambda, 3, 0 and 7 minus lambda. Now all we have to do is set the determinant of this thing to 0. Alright. So let's do that. So we start with the minus 1 minus lambda, 3, 0 and 7 minus lambda. So we multiply the diagonal terms first, computing the determinant. Alright. So solving this, we will get lambda equal to minus 1 and lambda equal to 7. Now we have the two eigenvalues corresponding to this matrix A. We have lambda 1 equal to minus 1 and lambda 2 equal to 7. Alright. Now let's say I want to find out the eigenvector corresponding to lambda equal to minus 1. Alright. So all I have to do is a minus lambda I times v equal to 0. Now I'll just put lambda equal to minus 1 over here. Alright. This will give me a minus 1 times I times v equal to 0. So this will in turn give me a plus I times v equal to 0. Alright. So all I have to do is solve the system of equations. So let's do that. Let me first erase this. Alright. Okay, so let's do that. So when I do a plus I times v, a plus I times v equal to 0, right? And we look back at a. So if we add identity matrix to it, we get a 0 over here and we get a 8 over here. So we get that 0, 0, 3, 8 times v equal to 0. Now we know that v will be a two-dimensional matrix, right? Because A is a 2 cross 2 matrix. So we can write v as v1, v2. So we can substitute the value of this general form of v over here. And you can compute this matrix multiplication and see that the equations that result out of it will be 3v2, v2 and 8v2 both equal to 0. These both imply that v2 equal to 0 is the solution for this system of equations. Now, we did not get a specific value for v1, right? So this means that there will be multiple eigenvectors for this given matrix. So v1 may take any value, any real number, any value along the real number, alright? v1 may be any value along the real number. So the general form of your eigenvector corresponding to your lambda 1 will be v1, 0, right? So any vector of this form will be an eigenvector for lambda equal to minus 1, alright? It will be a good exercise for you all to try out and find the eigenvectors for lambda equal to 7 using the methods I followed here. But you can look at like again analyzing this vector. If you however want a specific answer for your eigenvector, you can plug in, let's say 1 over here, and this can be reported as a very valid answer. Even 2, 0, 3, 0, minus 3, 0, any vector like that would be an answer for this problem. All right. So I hope it was clear. Thanks a lot. This is Saad from IIT Bombay. This is 9pointer.